All right, so we are at a very exciting point in the class now, where we are now ready to involve the full aspect of dynamics. So what I have here is what we've done so far, and kind of a reminder what we did, what we talked about on the first day. So far we've focused on kinematics, where we're describing motion, position, velocity, acceleration, many different coordinate systems for different types of motion, right? Just relating these quantities based on given information, right? Describing that motion, knowing that forces cause motion or causes the change in motion, but not worrying about it at all, right? Dynamics comes in that we actually start considering what those forces are and how they relate. So going forward, we're going to be focusing on the kinetics part, which is when we're extending the kinematics. And so a part of these problems is going to be, okay, so kinetics is studying the forces that cause the motion as governed by Newton's second law. So think, right, these are the forces, this is the energy involved, kinematics is then the motion, and together the two of them combined makes up dynamics. This is dynamics. All right, so Newton's second law, remember, is where we sum the forces external to a body, to a particle, to an object, whatever you want to say. Here, your statics course talked a lot about this. In fact, statics is when this equals 0, nothing over here, right? And now we've gone into great detail of the kinematics of a particle, right? And so the analysis techniques we're going to study are force, mass, acceleration relationships directly out of Newton's second law. We can modify this relationship to talk about what work goes into a system and the energy associated with it. So we're going to turn this left-hand side into the work and turn the right-hand side into energy. And what we do there is we turn this vector equation into a scalar quantities of work and energy. And it's just another tool to analyze the kinetics, well, really to analyze the dynamics of a system or a particle. And then the third analysis technique is looking at the impulse and the associated momentum. Again, we're just going to be turning the left-hand side into this thing we call impulse and the right-hand side into this physical quantity we call momentum. And they all stem out of Newton's second law. I mean, I couldn't put enough boxes around this. I couldn't, if there's anything you can get out of this class, any of your mechanics classes at all, is this relationship and how versatile it is to analyzing engineering systems. Now we need to do this for these three different coordinate systems, right? We didn't just introduce the coordinate systems just for just for fun. We actually use them, and again, these are choices that we make in analysis to then, kind of like how the analysis techniques themselves are choices we make in analysis. These are the three different coordinate systems that we will choose to represent the motion, choose to represent the forces in these coordinate systems based on the convenience, based on the geometry of those systems. Okay, so we'll get a blank page here. Let me zoom in a little bit. Come on, find it. There we go. Okay, so let's get into it. So chapter 14, and you can see when I had those three different techniques, there was like different numbers there in the boxes, and those are referred to the chapters in the book. So we're going to start, and that's all of this lecture is on force, mass, acceleration relationship directly stemming out of, so you might hear me say this, FMA, right? It's just what is the relationship between force, mass, and acceleration? Really, it's just Newton's second law in its direct glory here, right? Summing the forces external acting on a particle, and that's the other thing, right? This class is composed into rigid. The rigid bodies are coming when we're a collection of particles. Right now, it's just individual particles, compressing all of the mass to a single point and watching where that goes, right? Or maybe think of the center of mass of a true object, or how does that act? Okay, 14.2 is then going to be Cartesian analysis of the force, mass, acceleration relationship. Okay, so starting easy here. All right, so we're going to take this vector equation and sum up the x components of all the forces on an object. That's in the I hat direction in our Cartesian coordinate system. Sum up the y components in the j hat direction. Sum up the z components in the k hat direction. And that's going to equal mass times acceleration. X component of acceleration in the I hat plus mass times y component of acceleration plus the z component in the k hat direction. All right. So let's see. Let's actually start on the right hand side of this equation. This is the motion. These are the accelerations. These stem out of our kinematics that we've already spent so much time looking at. These stem out of the kinematic relationships intrinsic to the system. Okay, I'm going to spend some time talking about here. This is the new part, right? What are the forces involved? This relationship we have here, stemming out of Newton's second law, really is three equations, right? Three independent equations. They could be coupled together here, but we can break this up component by component in Cartesian, right? Summing all the forces and their x components is equal to the mass times the resulting acceleration in that x direction, right? The x component of acceleration. The y forces sum up to give us a relation to our y component of acceleration, and summing up the z components gives us our z component of acceleration. Okay. Now, that leads us to what are all of these forces? Okay. How do we analyze them? So I'm going to try to get to examples as soon as possible here. I think that's the way to do this. I think we have some experience from our statics class on doing this. So I'm just going to highlight some key characteristics and then we'll get into the examples. Okay, so we need free body diagram is going to be the tool to analyze these forces. That includes all external forces acting on the object, the particle, whatever it is that we're analyzing. Okay, that'll be the key. This is the one. Okay, let me spell it out this one time. Free body diagram. What we mean by that is we're isolating an object, and instead of the complexity of the system around it, we just draw the forces on the diagram and use that as an analytical tool. And then the free body diagram acts as component-wise breakdown of the more complicated vector nature of the forces and of the Newton's second law relationship. Okay, so it's really focused on the forces, though. Sometimes you'll see this as a force body diagram. Free body diagram is going to be required for these kinetics problems. What I mean is, don't let yourself work through one of these problems without first drawing a free body diagram. And in fact, there might be many of them in one problem. Okay, so let's just make a list of the general approach to one of these kinetics problems, and then we'll just jump into problems as soon as possible here. Okay, so maybe think of these as tips for a thorough, useful, accurate is something we're trying to shoot for, force body diagram, free body diagram. Okay, let's do step 0. I don't know why I'm starting at step 0, because this should be intrinsic. So we choose and label a coordinate system. That's actually done before we even start. Okay, that's now step 1. That's already in there. So in this case, right, we're Cartesian and it's spelled out. Pretty obvious. Okay, step 1 is then going to be to isolate the object. Step 2, replace the supports with appropriate forces, whether known or not. Usually they're not known for supports. Okay, and so supports, right, these are pins, a roller, maybe it's fixed, and then that, right, so roller has a force in one direction, pin has kind of forces in all direction, and then fixed has force supports and a moment preventing it from rotating as well, where pins and rollers can rotate. Okay, 3, sketch the applied forces. Okay, these forces are could come from friction. Actually, that one we often neglect. We could have a spring force. We could have the weight due to gravity. Whole bunch of other ones, right? We're going to actually talk about some particular forces as we go along here. And then make sure on our free body diagram we're labeling the dimensions and the angles that we have known and anything else that's going to help us, have the geometry we acquire there, right? Maybe we don't need to put like the acceleration and velocity, but by putting in lengths, right? Because the lengths actually, if there are lengths, but especially angles are going to help us determine the components of a force from its true vector nature. Okay, so let's jump into first example here. All right, so in this first example, first kinetics problem here, example problem, in the Cartesian coordinate system, we have a mass of mass 1.8 kilograms attached to a spring with spring constant 80 Newton per meter, and it's currently in an undeformed state, so it's in its equilibrium position, not stretched, not compressed. It's providing no force right now. It's then released, right? So gravity is going to act on the mass to pull it down. While it's being pulled down, we're stretching the spring, which is then going to pull back up on the mass, and at some point it hits the floor. Maybe if the string was stronger, it wouldn't ever hit the floor, but this one will. We want to determine the velocity when the mass hits the floor. Okay, and I think everything's on there. We only need to drop 0.3 meters to hit the floor. Okay, here we go. First step in our kinetics problems, and you're going to see me being very consistent with this, is drawing a free body diagram. Even when we have intuition, we're still going to draw the free body diagram to be completely consistent and careful. Okay, our x-coordinate, only one dimension needed here. We'll just have it straight down from the center of that mass. Okay, we have a spring force acting upward as the mass drops, and we have our gravitational force acting downward as the mass falls. Okay, and that's pretty much it. Okay, now we go to our equations of motion, right? And this is the governing equation, so let's write this out. Equations of motion, and we're getting into now where we need to really have all of these steps in these problems. All right, there's a free body diagram to analyze the forces. Equations of motion are going to be the way that we tie together the forces and the kinematics. And the kinematics, so the kinetics up here, tying together kinematics and kinetics. And then if we need to, we'll have a kinematics analysis later on. Okay, so another way to call these equations of motion, and maybe the equations, if we're talking this in a general, maybe we'd only need one, which we do here. This would be another way to describe this. These are the governing equations. How, what governs the system and its response, or how it evolves in time. Well, that's Newton's second law for our purposes. So if we sum the forces in this vertical x direction, that should equal our acceleration in that direction. Okay, we sum the forces from our free body diagram. Well, mg is acting downward, which is our chosen positive direction for x, right? We're free to choose that all we want because there's only one direction of motion. And kx is then restoring, trying to bring us back to the undeformed state of the spring. And that equals mass times the acceleration in that direction, right? Okay, so that's all good. We did kinetics. That's this left-hand side. On the right-hand side, we now have, so this is the kinetics portion from our free body diagram with our forces. Now, over here, we need some kinematics work. Okay? To get velocity, which is what we need in the problem statement, right? Determine the velocity when the mass hits the floor. To determine velocity, we need to express ax as, well, that's dv dt, right? But it's going to be advantageous to express it in terms of dv dx, dx dt. Remember, this is just the chain rule expansion here. And this is because our forces, right, this left-hand side is not a function of time. It's actually a function of position, right? This is a constant. It doesn't care where we are in x, but this is a function of position, right? None of these change as the mass falls. This is the thing that falls. Okay, we should be careful with our m. Let's keep this general here. No, let's change it. Might as well, right? This is actually for our mass. This is maybe a general form of it, but we labeled this as a capital M, so I should be consistent. Okay. Notation. I'm very much a stickler about it. Okay. So the reason we're doing this is because our left-hand side of the equation, that sum of the forces in the x direction, is written as a function of x, not of time. All right, so that's what drives this decision to express it this way. So a of x is v dv dx, because dx dt is velocity. Okay, great. So we take this relationship, and we have v dv dx equals, now we're going to rearrange our Newton's second law here, right? A of x is now what we have over here. Divide the left-hand side and switch it to the other side. So divide it by g and flip it to the other side. Divide it by m and flip it to the other side. So all we have there is a g. And then we have a k over m x. Yeah. And now we do that thing where we need to integrate this in x. dx integral from 0 to 0.3. Right? As we drop from the initial state, x equals 0, to x equals 0.3, where x is defined downward. Okay, so if we do that to the right-hand side, we do this to the left-hand side of our equation, sneak it in there, and we have 0 to 0.3. Okay, but as we've done many times in the past, this is just a transition into the velocity, and if we do that, we just need to change the bounds to the velocity. And so this is the initial velocity. Well, the initial velocity is 0, and then this is the velocity at time, well, sorry, when x equals 0.3, when we hit the floor of dv equals, and now we can actually do this integration here, which is gx kx squared over 2m. Oh, that's, sorry, I forgot a subtract sign. Okay, I think that's all good. Kind of one step behind on the left-hand side, so this is going to be v squared over 2, and I'm going to kind of lose these brackets, right? We're looking for the velocity squared here. Velocity squared over 2, and then we'll just subtract off the initial velocity, which is just 0, right? And then now this right-hand side, the top term is going to be, or sorry, the bottom bound is just going to be 0 because those all have x's in it. So you know, we could actually plug these in. We will have a value of, let's see, g, which is 9.81. 0.3 minus 80, 0.3 squared over 2 times 1.8. And now these all have units. We can actually check the units independent here, because these should actually work, right? So this is meter per second squared. This is meter squared per second squared. Yep, that's a velocity squared. This is a Newton per meter. This is a meter squared. This one we're dividing by a kilogram, so there's a conversion of the Newton. Remember, a Newton is a kilogram meter per second squared, so let's do an extra unit analysis down here. We have kilogram meter per second squared times meter squared, and then divide by a kilogram. The kilograms cancel there. And oh, and then, sorry, and then there's another meter there. That's a Newton per meter. So that was a Newton. So there's another meter there. Newton per meter is kilogram meter per second squared. That's a Newton, but divide by a meter, right? So those meters cancel. And after all this, we get meter squared per second squared. You know, we're just confirming to ourselves that this is a velocity squared check. Okay, I'm happy. Units check out. Great. Okay. And then we're just ready to solve this, yeah? Plug in all those values. You got to multiply through by the 2, so be careful to do that. You should find that V equals 1.3733 meter per second. Okay, and this is in the downward direction, right? Because of the x direction. In fact, I guess the right way to say this, well, if we called it x, this is really in the I hat direction with our chosen coordinate system. So really, velocity vector is 1.3733 I hat meter per second. That's the velocity, right? And I just looked back at the problem statement to make sure we answered everything. It's asking for velocity, not speed. Speed is that. Velocity is in the I hat direction because of the way we defined the x coordinate, right? This is fine. This is what we wanted to get to with a little bit extra talk of our coordinate system choice. Okay. All right, so in the second example, we have a kind of a fun-looking system here. We've got a block sliding along here where we're going to neglect the friction, and we got a so we got a cable pulling down with a pulley here, such that when we pull down, right, there's going to be the block connected with its support there with the pulley there is going to feel a force both up the slope in that tension and also downward. Right, so kind of a little bit down the slope as well, but really straight downward with this P, right? So that helps visualize here as we start with, as always, a free body diagram. Let's go to just represent the block as just a single point, and we'll put some forces on this. We'll also put our coordinate system on this. Okay, so the chosen coordinate system, by convenience, is going to be straight up the slope, okay? So this will be our I hat and our j hat, and in doing that we are choosing this axis to be x, and perpendicular to that is y. Okay, and let's see what forces, what color should we do the forces? In green here, let's say, okay? So we've got the normal force, which is always perpendicular to the surface, and x defines where the surface is, right? P is going to go straight up the surface. That's from the tension in the cable going up, and then we also have one coming straight down as we're pulling straight down with P as well, right? So that tension in the cable gets both of those contributions, it sort of gets turned over there, right? The other thing we want to put on here is always angles. So this with the horizontal is theta, and then this is a 90 degrees, so this is 90 degrees minus theta, and then this is also 90 degrees horizontal to where P is, which is straight down, so there's theta again. So we got this theta going every other. Okay, that'll be important for our analysis here, dimensions. Now I've missed one force, right, which is the weight. I think that's it, right? There would otherwise be friction here if we didn't neglect it. Okay, we're neglecting friction. Okay, so let's take one of these forces. I mean, you know what the next step, right? We're going to decompose our forces into their components. Trivial for P, trivial for N, not so trivial for P and the weight. Let's just do it for one, and the other one will come naturally. So P, the applied force, this P I should say, the downward one. So any of these downward forces, right? So this is P. Let's put our coordinate directions, the y one on there. Right, and then here is theta. So to get to the components here, we need to project this perpendicular, okay? And there is one component, and here is our other component. So this is the y component here, right? So we have the, I should say, right, separate this from that. We're just focusing in on this like little part, this is Py. All right, that's the component in the y direction, which is going to be a negative quantity. So if P is the magnitude of the force, minus P cosine theta, as it's adjacent. And this one here is the x component, which is also negative, minus P sine theta. Right? Just this is a positive x direction, positive y direction by choice. Okay, and the same thing would happen for weight. So the mg in the y direction is minus mg cosine theta and an x. Okay, so let's now go to our equations of motion. And what we want to do, right, is determine how strong we have to pull on P to get a certain acceleration up the slope. So we only need to look at our Newton's second law in that direction to get to acceleration in the x direction. All right, well, it's just trivial that in the y direction, really just the y direction would tell us what n is, right? We don't know that. We have information on everything else, or the relationship. We want to know what P is to have a specific acceleration here. So that's going to be given by just analyzing this, and then the y direction will give us what the value of n is. Okay, so summing the forces in the x direction, well, we have P heading up and all of P in this one. And then we have these x components for weight and the other part of the cable, right? The one heading downward. So we have an mg sine theta being subtracted off, and we have a P sine theta being subtracted off. And all of that should be mass times acceleration in the x direction. Okay, so for part A, we impose that we want the acceleration to be positive 2 meters per second. Maybe isolate that P has a 1 and a minus sine of 20 degrees. And that should equal mass times acceleration. So 0.2 kilograms. Acceleration is 2 meters per second squared in the x direction. Plus, and I pulled this term to the other side, that also has a mass in, so we have this inside the parentheses, 9.81 meter per second squared times sine of 20 degrees. And plugging in all those numbers, divide by 1 over 1 minus sine of 20 degrees, and we find that the P required to do this is 1.6278 newtons. Okay, I'm going to, just to make sure this fits on here, it's always hard to know where the screen ends, we'll just chop it off at one less unit, or one less significant figure there. 1.628 newtons. Okay, and then moving into B, luckily we've kept everything general until we got to this last bit. So we just do ditto here, all right? So now, oh, sorry, this problem statement is redundant. Oh no, down the slope, that was right. Don't even trust my former self here that I wrote the same thing, right? It shows down. So what we need to impose here is a negative. So for this first one here, right, we're imposing AX equals positive 2 meters per second squared. And now for this part B, we need a negative 2 meters per second squared. So all that's going to change in our calculation is, you know, ditto here, except this is now a negative 2 meter per second. Other than that, the same exact calculation, right? And we find a applied force of 0.4119 newtons, which might be surprising in that we went, you know, basically you need to pull down. But if you think about it, you need to pull down whether it's going to accelerate upward or downward. If you're not pulling at all, right, the thing's just going to head down at some acceleration. We could determine what that is. I'm just realizing now my J hat didn't even make it on the screen. A long time ago. Okay, now, at least the screen I can see. Now, if we pull strong enough, right, that's going to pull strong enough. That's going to cause it to accelerate upward, right? But if we still pull down, right, we could be breaking it from kind of its free fall down the inclined slope. And that's basically what we're doing here in this case. We don't have to pull very hard. We're just kind of putting a brake on it as it would naturally fall in its free fall. Before we wrap it up, maybe we do add the little note here about what happens in the y directions. We only analyze the x direction here, right? When we sum forces in the y direction and balance that with mass times acceleration in y, well, we know it's not going to accelerate in y. It's going to stick to the surface and either flow up or down. Okay, and what we're doing with that imposition here is being able to then find what the normal force is, right? Normal force is going to be, well, you have the only other y forces are p and mg in the cosine projection here, and then if that equals 0, then the normal force is going to be p plus mg, all of that times cosine of theta, and right, and then if there was friction, right, maybe you'd have to do this first to get a relationship for n with the applied force, put in the friction with some friction coefficient, and maybe it's a way to make this more complicated. But we'll leave it there. Okay.